Okay, so in this video, we're going to look at how to calculate single-slit diffraction patterns. And the formula that you have in your data booklet is this one, d sine theta equals n lambda, a very important formula. Some of you use this on your end of your exam, even though we didn't cover it, which is pretty cool. And I'm sure that you've seen it on some videos. But this formula actually is used to derive Young's double slit formula as well. So it's a very important formula. All right, and we'll be able to predict the angle of diffraction, so the angle right over here, based on the slit width d. So that little d represents the width of the slit. Theta represents the angle of diffraction. We'll talk a little bit more about that in a second. And lambda represents the wavelength of the light coming in. All right, and n represents the order. Okay, so for example, this is the first order minimum, first order maximum. Okay, we're going to figure out what that n means in a second. All right, now for single slit diffraction, what you need to remember is this formula is for destructive interference. That's important. So the formula is used for destructive interference. And you need to write that down in your data booklet just to help you out. Okay, so just to remind us of what the diffraction pattern looks like. When the diffraction pattern is formed, you have a very bright spot in the middle. That's called my central maximum. And then you get these series of bright spots appearing mixed with some dark regions onto the flanks, onto the side. And these are called first order maxima, second order maxima, third or first order minimum, second order minimum, or third order minimum. Okay, and this blue triangle in here is what's important for that formula. So I'm going to pull down over here and show you a diffraction pattern I generated with a red laser. And I shine the red laser through a slit that has roughly the same width as the laser, or a little, it's close to it. So let's say this is 0.01 millimeters is my slit length. Okay, so d equals 0.01 millimeters. Okay, what I would end up seeing on the wall, if you were in the class, you would see this being formed on the wall, a diffraction pattern. This is my screen. And what we would do is we would measure the distance from the wall to where that slit is. That's the distance. I'm going to call that capital D, my distance to the wall. And I would ask you to then measure the width of the central maximum. So you'd measure the width of that central maximum. And if you measure that half width over here, I'm going to call that my half width of central max. What you're going to get is two dimensions over here that would allow you to calculate your angle of diffraction. So when that theta represents the angle of diffraction, the angle between the center of the central maximum, okay, and the center of my slit that is causing diffraction, and the first order minimum. So I'm going to highlight that. Okay, so remember, it's my first order minimum. Okay, so if I would take the half width, let's just call this x, that variable. So if I take x, my half width, okay, opposite over adjacent, that's going to be equal to tan theta. Okay, so tan minus 1 x over d is going to give me my angle of diffraction. So that's my angle of diffraction that we use for the formula. Okay, and so that angle of diffraction is something that we can measure in an experiment. You'll be doing that in an assignment very quickly. You'll be measuring the angles of diffraction. So for single slit diffraction, we're looking at destructive interference. You're looking at the angle to that first order minimum. So you're measuring that angle, and that's your angle of diffraction. And then you can then plug these variables into the formula d sine theta equals n lambda to be able to calculate whatever you want. So as long as you measure your angle of diffraction, okay, sine of that angle of diffraction times d, the slit width, would give me, for example, the wavelength. I could measure the wavelength of a laser in an experiment using this formula. And n in this case, because that's my first order minimum, is 1. Okay, so I can use that formula to measure the wavelength of a laser. On the other hand, if I had the wavelength of the laser, for example, the wavelength of a green laser is 540 nanometers in the lab. We have that. Okay, we can measure the angle of diffraction via an experiment, and that would allow us to calculate the size of a hole that we put into a piece of paper or whatever you want. Okay, so that's how you would use that formula. Okay, but nowhere in all this stuff do I see sine. Where does sine theta come from? Where does this formula actually come from? And so what I want to do right now is I want to derive this formula. How do we derive that? Where did that come from? D sine theta equals n lambda. Okay, and it comes from geometry. Okay, and it comes from Huygens principle. So I'm just going to change the color here. So remember, all these diffraction can be explained by Huygens principle, whereby all these points inside of that slit generate wavelets. Okay, these wavelets form, and when they get to a point, okay, they will interfere either constructively or destructively. Okay, in this case, because we get a black spot over there, no light, that means it's destructive interference. So if I'm taking a look at that wavelet forming a wave and going over here, and that wavelet forming a wave and going over here, what I would see is that in order to get destructive interference, the path length difference, okay, so if I draw this line over here, that's where they would intersect, okay, and this extra bit right over here, if I look at that extra bit, that's my path length difference. So remember, for destructive interference over here, destructive interference, the path length difference has to be 1/2 of a wavelength. That means that this wave traveled 1/2 wave longer so that a trough overlaps with a crest and destructively interferes. Okay, so once I have that, I know that I have a 1/2 wavelength being that little line over here, and this line on this side is d over 2, okay? And then I can draw an angle here, okay? Well, that angle in that right-handed triangle, that right triangle over here, this is a 90-degree intersection. This line's perpendicular, so that's 90 degrees. Okay, so if I would draw this out, I'm going to draw that triangle out right over here. Okay, this is my opposite side. That's my hypotenuse. I can say that sine theta is equal to d over 2, no, opposite over hypotenuse, sorry, is equal to 1/2 lambda divided by d over 2, okay? So you can see that. And I can see that I can cancel out the 1/2s, okay? So this 1/2 divided by 1/2 over here cancels out. And I'll be left with sine theta is equal to lambda over d. And then I can move that over out of this side, cross multiply, I'll get d sine theta is equal to lambda. And where does the n come in? N comes in with the order. Okay, so this is the first order minimum. The next one here would be the second order minimum. So for the first order minimum, n is equal to 1. So if I put an n here, that means I just have to put a different number for the order. 1, 2, 3, 4, that would be my order of diffraction. Okay, so that's how we get that formula d sine theta equals n lambda. So you can measure in an experiment, you can measure this. Okay, you can measure the half width of the central maximum, you can measure the distance to the screen, and you can do a little trigonometry to calculate that angle. But another little trick is, if that angle is very, very, very small, let's say like less than a degree, if that angle happens to be very, very small, then what we know is tan theta is equal to sine theta at small angles. Okay, that's an important thing to know. Okay, so sine theta then becomes in this case, sine theta then becomes the ratio of my half width, so I'm going to call it x over d. Okay, so I can just plug x over d over here times d is equal to n lambda. Okay, and then I'll be able to calculate the wavelength of a laser or whatnot. So in the next little video I'm going to make, we're going to practice doing some calculations with diffraction, but it's not a bad idea to stop this video, go back to the beginning, and see that you're able to derive this formula. You're able to pull this out. It's really important that you're able to draw these triangles, okay, that are in here, and you're able to explain how this diffraction pattern forms by interference, okay, and the law of superposition, and you're able to draw that triangle, and you're able to draw that triangle, and come up with this relationship. That's a question that comes up all the time in exams. So then you're going to have that on a problem set. So make sure you can go back through this and draw this up. Okay, thanks.